In this video, I'll explain how to create and fine-tune an AI avatar. Yes, I am an avatar of Ronan, created using only a starting image and a voice recording. You'll be able to do the same, whether it's for a conversational assistant or for entertainment purposes. I'll then show you how to further improve quality by fine-tuning the model on a series of videos of yourself. Let me start by describing the simple avatar pipeline and then the full avatar pipeline. In the simple pipeline, which is what we'll focus on today, we're going to take an image and a voice recording, feed those into a video model called MEMO, that's the model we'll focus on, and create a video. Now you can do an even more complete pipeline by creating the image or the voice recording using models themselves. For example, you could start off with a text description of the image you like, for example, Ronan within a newsroom, and pass that to a diffusion model that has been fine-tuned on your appearance. That's something I do cover in my diffusion model video on Flux, so I recommend taking a look at that if you want to be able to generate the image using generative technology. You can also generate the voice recording starting with a transcript if you have a text-to-speech model. Now, you could use a text-to-speech model for somebody else's voice, or again, you could use a model that is fine-tuned on your voice, such as Style TTS2, which is what I covered in my fine-tuning video earlier. So yes, you could generate this output video starting just from a text description and from a transcript if you use these three models. But as I said, this video is going to focus on what's new to this channel, which is taking an image, a voice recording, and using those to generate the final video. Now I want to explain how this MEMO model works. I'll go through the paper a little bit later. How to generate zero-shot avatar videos from image plus voice. This means just generating a video without any fine-tuning of the model. You just start with an image and your voice. And then I'll describe the more elaborate approach where you can actually update the weights so they're more tailored to your specific appearance and your voice. Now, to understand how MEMO works, or MEMO, I'm not sure which way they pronounce it, you can first start by understanding image diffusion models, because video is just a small step from there. So I'll briefly recap on how image diffusion works, and then I'll describe how it works for videos. In image diffusion, you start off with a series of clean images for training. So imagine a corpus with, thousands, millions, billions of these clean images here. And you intentionally add a small amount of noise to each of the images, just like this here. I've added in some Gaussian noise to the image. And now with this noisy image, we start to train a model to be able to predict what the noise is on this image. So we take the image, we feed in some text describing what's in the image to the model, and this is a bunch of weights set up in a transformer type architecture with attention, and we get the model to predict what the noise is on this image. And when we have the prediction for the noise, we can compare the noise, we can compare the prediction of the noise to what the actual noise was, and we can use that then to update and improve the weights within our model. So you can see here how taking a large corpus of images, adding random amounts of noise, we can get to having a model that's able to predict the noise if you give a noisy image. Now, how this works then when it comes to generating images is we start off with some kind of noisy image, or actually we start off with pure noise if we want to start from scratch. We feed in a description of the image we want, and then our diffusion model is able to predict the noise. And if we can predict what the noise is in this image, then we can subtract the noise from the starting point in order to diffuse out towards our clean image. Now, I've just shown everything in one single step, but in practice with diffusion, you diffuse in multiple steps. So you start with pure noise, you feed in the description, you try and predict the noise in this image here, and when you have that prediction, you subtract it to get a slightly cleaner image. And by repeating this, you can get towards a clean image. So here you can see 3 steps, or rather 2 steps. What we will do today will typically be, I think it's 20 diffusion steps. So often you will do this in smaller increments in order to more cleanly and robustly move towards this clean final image that you want, which by the way is all the time conditioned on these keywords here. So that's a very quick overview of how image diffusion works, and video diffusion is just a small step from there. So instead of diffusing out one image, as we do in image diffusion, and sorry, I've repeated the word there. You see now why I did do that. Instead of doing this as you do in image diffusion, you will pass in multiple images multiple noisy images, and they will represent time steps. They'll represent frames in the video, and you will predict the noise for 3 subsequent frames. So this is the main improvement to get from image diffusion to video diffusion. You simply kind of parallelize, so you have multiple frames being predicted, which requires you to pass in multiple noisy latents or multiple noisy images in the input. In practice, this means really doing the same thing as the image model, except you concatenate the matrices. So your input is now just not an input for one 2x2 grade of noise. It's now the concatenation of 3 grades. Concatenation just means putting them together in a line, essentially, in matrix terminology. So we will now diffuse out multiple images, and you can imagine that we can predict the next, say, 15 frames. And once we've the next 15 frames, we can go on and iteratively predict future more and more frames. Now, the second thing we need to do is feed in the audio, because remember, this is a talking head, and a talking head needs to move its lips and head ideally in line with the audio. So we also pass in the audio here, which you might have recorded. That's what I'm doing. Or you might generate using a model like Style TTS2 or something from, say, 11 Labs. So in addition to conditioning the model on, say, dog cartoon, we would also condition it on some audio here. Now, the third thing we do to adapt this avatar model is we condition it also on a reference image. So both during training and inference, we're saying, when you generate these output frames for the video, we want you to generate them with this reference image in mind. And that keeps the model gravitated towards that reference image in what it's producing. And lastly, to improve the video performance and the smoothness, it also makes sense to condition on the past frames. So we don't just want the model to produce based on a reference image, based on audio, based on text. We also want the model to condition based on past frames. And that just allows it to be smoother because the model is taking into account, okay, well, the last 15 frames had the head moving this way, so probably the next few frames should continue, at least in some vein, to have that movement captured. And by the way, at this point here, because we've got audio input, reference image, noisy latents, and the past frames, we don't actually have to define or allow text to describe the image. There's no reason why you couldn't have text influence the output of the avatar video. But in the case of MEMO, it's not guided by text. It's just guided by the reference image, the audio, and the past frames. So this is an overview in simple terms of how you get from an image model to a video model. Let's take a look now at how the paper implements it. So this might look a bit complicated. It's the diagram from the MEMO paper. But let's start by looking at the inputs and the outputs, and then I'll describe what's inside, and you'll see how it maps to the simpler representation. So in terms of inputs, we have the audio, which I mentioned before. We have the pass frames. Here you can see 4 pass frames. Actually, we'll use 16 pass frames when we do inference. We have the reference image. This is the snapshot you take of yourself in order to generate a video based on it. We have the noisy latents. And then on the output side, we have a sequence of frames. So we've got the output frames, which, as expected, will help us to build up the video. And as I briefly mentioned, the way this works is kind of recursively. So we'll start off, generate the next, I think it's 16 frames. And then when we have 16 frames, we'll go back again and we'll feed that back in here as the past frames, and we'll generate more output frames, and we'll progressively be able to get to creating a longer and longer video in that way. Now, there's one other input that I didn't describe in the simple model, and that's this memory bank here. The reason for this is because we recursively generate, say, 16 frames at a time. This means there isn't a way for the last 16 frames, or say even the middle 16 that are being generated, there's no way for them to have knowledge of what happened earlier in the video. And this is a problem because ideally later parts in the video are somewhat dependent on earlier parts of the video. Now, typically in transformers, the way we would capture that is through attention, and you could build the architecture that way. You could have you could always attend to the past frames, but that will take up more memory and more computation. So rather than doing that, there's this kind of a knowledge storage that's happening here in memory. And it's effectively kind of it is linearized. It's not quite a purely linear attention approach. It reminds me a bit of long short-term memories, LSTMs. But basically you have this series of matrices, that is continuously updated, and it stacks up information based on the past frames that were processed. So you can think of this as a way to remember what's prior to these past frames that are being passed in, because the past frames we passed in are literally just the recent past frames. So that describes the inputs. We have 4 here, the memory, and then the outputs. Just a quick note on these encoders and decoders. These are here because we do not actually diffuse images per se. We diffuse vector representations of the images. And so when we have any image inputs, we first convert them into vector space, into a latent representation. We work then with those arrows as we go through these diffusion models. And then on the other side, we convert back from the arrows into real images. So that's why we have encoders to go from images to vectors, and then back from the final predicted vector to the image here. So that leaves us now with these 2 middle pieces here. And you can interpret this large one here, the diffusion net. I mean, it is a diffusion model, as I've described before. And simply what it does is it takes vectors coming in, combines all the information of the inputs, and then transforms those vectors into typically a narrower vector representation. So you might start off with a large vector dimension. It will narrow it down. That's why this looks like a funnel, into a more compact representation. And then it will expand it out again into a more granular representation before it's decoded out. So this is kind of forcing the model to represent all the information in a compact way, and then bring it back out again to a granular way that's interpreted by humans here as images eventually. And if you forget about this reference net here, really this corresponds to the diagram that I showed here. You've got one big diffusion model. You've got all of these inputs here. You got the 1, 2, 3, 4 inputs plus the memory then. And then that's allowing you to essentially predict noise, which effectively allows you to predict images. Now there's one difference here, which is the inclusion of a reference net. Basically, the way that these past frames and the reference image are included in the main model, it's not a straightforward input that's combined at the start. It's actually introduced as information throughout the layers. So this image information itself is going through a diffusion network, which is then feeding in parallel to the diffusion net here. And the idea is that you want to have the images influence every step of the kind of compression and expansion of the video information. Now, I'm going to speculate that maybe you could get this to work just by passing the information into the start rather than passing it in parallel. That's something we've learned from multimodal models when we try to add in image information to text LLMs. But I'm not confident in that because I haven't run the ablation. Suffice to say, this is a more complicated way of adding in information from the images to the diffusion of the video information here. So with this, we're ready to move and create some examples. We will start by not the training, but the inference part, just generating some videos, given a reference image and given some input audio. I should note that what happens when you start off with your first iteration of generation, you have no past images. You just have taken a photo of yourself. You've no past images. Well, the default there is typically to just copy paste that first image as the past 16 images. So the very first time around, you just use the same image as the past images. Now you could argue that might lead to a lack of movement in your video, but that is the convention. And from there on, you do have past images and you can use those in order to seed and generate the next videos iteratively, or the next frames iteratively. For the next part of the video, I'm going to show that inference and fine-tuning, and I'll be working out of the advanced inference, the advanced vision repo. So you can get access to these scripts. You can get membership via trails.com/advanced-vision. But I will put a link to the original open source repos, the models that this video is based on. And I'll try to describe enough so that you could follow along by building things up yourself in Cursor if you don't have the resources to get the detailed scripts I show here. So I'm going to git clone that repo into Cursor, but actually I'm going to do that on a runpod hosted instance because I want to run these scripts on a GPU. I'm going to start off with my one-click fine-tuning template. This is an open source repo, Trellis Research on GitHub, one-click LLMs. So I'll just click here and it'll give me a template. I'm going to select the H100SXM for the fastest speed. And yeah, this is the template here. It's a CUDA 12.1 template with PyTorch pre-installed. And I'll click here to deploy on demand. Now, once this pod is up and running, I'll connect in Cursor actually, and I'll clone my Advanced Vision repo. So the container is now started. I'll go to SSH. I'll copy the SSH connection here, go to Cursor, and now I'm going to connect to host, add a new host here. I need to make sure that I have the right SSH key. So you will need to go to Cursor, rather RunPod settings, and put in your public key if you want to connect via SSH like this. I'll add it into my SSH config file and connect. And there shouldn't be a password requested when you connect to a RunPod instance. And next, rather than opening a folder, I mean, there are no folders yet, I'm going to git clone. And one of the easiest ways is just to use the clone repository command here. Clone from GitHub, type in the repository, research, and then Advanced Vision. And you don't want to move too fast here because sometimes it will pick the wrong repo. And I'm going to clone that into my workspace folder. So in this repo, there are quite a few things. There's the ability to train diffusion models, to fine-tune diffusion models like Flux, the ability to train vision models like QuenVL, including the 2.5 model, and many other vision models, including for bounding boxes or object detection. There's details on data preparation, running servers, but today we're focused on AI avatars. So I've moved to the AI avatar folder here. And next I'm going to just open up the README within this folder because it'll help us guide through what we want to cover. Now, first thing to do is to clone the repo, which is available at MEMO avatar/MEMO, and install the requirements. So I'll just open up a terminal here and run this. Notice that I'm using UV, which is a faster way to install than pip. So I install UV, create a virtual environment with Python 3.10, and then install the requirements that are within the MEMO repo. Now, there are a few other things I'll install too. HF transfer is for fast weight download. Dcord, I think, is to do with sound, and FFmpeg. This will help us with converting videos and resizing videos, for example. This is the environment variable to set for HF transfer for the fast weight downloads. So basically, we'll now have MEMO downloaded within AI Avatar right here, and this will give us the basis for running some of the core scripts. Now, the key scripts here are going to be running inference.py and finetune.py, and there are versions of those available directly here in MEMO, finetune.py and inference.py. But I have updated the scripts to provide better logging in the case of inference, to provide some extra care for sizing the images and the videos. And then for fine-tuning, I've provided a LoRa script, which I'll talk about a bit later. But basically, I've put all of these scripts not within the MEMO folder, but I've put them here. You can see them listed directly in the AI Avatar folder. And I've then created a script that will allow you to copy these contents into the cloned repo so that when you run the normal commands here, it'll actually run the updated Trellis version of the scripts. To do that, I'm going to first use this Trellis script, which is called copytrellis.sh. And this, as I said, it's simply copying the Trellis versions of the scripts into the MEMO folder. So let me go back to the README. I'm giving permission to run that script. And then, I need to be first in the correct folder, which is actually the AI Avatar folder. And then I'll run the script. And that should have copied. Yeah, it's basically copied all of the Trellis specific files into the MEMO folder so that we're now able to run those scripts handily. So first thing I'm going to do is create a small video. And I'm going to create it. I'm going to create actually the video that you saw at the start of this video here. I know that's pretty meta. I'm now ready to start doing inference. And there are two ways to do inference. Well, there are many ways, but let me describe two ways to get set up. The first is simply to go to the MEMO folder here and go to assets and put in an image and then put in some speech, put in some audio. So here there's a sample image. It's Leonardo DiCaprio. And here's a sample speech, which is not Leonardo DiCaprio.
And I will strike down a...
But if you run the script just in base form, then you're going to get a video of Leonardo DiCaprio talking. I think it's maybe a line from Shakespeare or something. I'm not quite sure. But if you just run that raw, you're going to get Leonardo DiCaprio speaking. Now, I don't want to run that example. I want to run an example of me speaking. And I've made a quick way, a quick kind of trick to do that. So I need an input image and I need to have input audio. And a good way to do this, if you're trying to train a model and see performance, is just start with a real video of yourself. So I've downloaded a real video of myself from Descript. It's actually a real recording of me doing the intro to this video. And using that, I've got a script that will convert it into an initial image and then the audio. So it will basically use the video to create an image and then create audio and use those to create an AI generated video. And that's done using the extract from video script. So first I need to populate the assets folder with that video. So I'm going to go to MEMO, assets, and then I'm going to drag in the video that I've downloaded. So I'm just going to put it in here, intro to avatars. And yeah, here you can see that video. And as I said, the script I'm going to run now is just going to grab an image from the start of the video. It's going to crop it to be square, and then it's going to create a video based on that. So here, what I'm going to do is go back to my README, and optionally then I can run pip install OpenCV Python and run extract from video. And what that should do is install, and I'll try run in the MEMO folder. And you can see, having run that script, I have now not just my video that I've uploaded, but I've got a clean screenshot from the start of the video. That's going to be the basis for my AI generation. And then I've also got this voice recording here. That's also going to be the basis for the generation. So with that done, I can now run Inference. So it's going to run inference.py, and it's going to make use of my input image I've just created and my input recording, and it's going to output it to a folder called ZeroShot. And this is ZeroShot because I haven't trained the model specifically on my semblance or voice. I'm just using the model as is based on my image and voice recording only. Now, there's one other file to check here, which is configs inference.yaml. And I should say that the inference.yaml file has also been replaced when I ran that copy trellis. So it's got the configurations that I recommend. So we've resolution here of, this is 512 pixels tall and wide. And these are square images. So yeah, it's best to crop your images to being square. I have some scripts later that automatically do that. We'll be generating 16 future frames per clip, and there are 30 frames per second. So that means to get 1 second of recording, we're going to have to iterate a little less than twice, because there's 16 clips generated each time. The number of pass frames we pass in is 16. The very first time we iterate, it will just be 16 of the first starting images, which is specified here as 16. And then the inference steps, sorry, I think I said that backward, but the pass frames are 16 and the initial pass frames are 16 as well. The inference steps are 20, so we diffuse from a noisy latent. So from a noisy arrow, we diffuse that in 20 steps to get to the clean representation. The CFG scale here is classifier-free guidance. Basically, when we provide inputs like the image, it's going to predict the noise, but you can also predict the noise without providing any inputs. So just based to kind of the reference of what is the average image or video that would be created. And what classifier-free guidance does is it considers the difference in noise predicted with inputs that's my specific face compared to the generic noise that would be predicted. And then it amplifies that. It amplifies it by a factor of 3.5 here. So you can increase this. Typically you have it somewhere between, I think maybe 3 and 7. I noticed if you put it up to 7, it creates issues with the coloring of the image. So probably needs to be somewhere between 3.5 and 5. If you put it higher, it'll tend to accentuate the aspects of me that are in the initial image, and audio to a lesser extent. This is the weight D type, so BF16 for an Ampere GPU or a Hopper GPU or later. You would use float 16 if you're operating on a T4 or something. In Collab, I don't know if it'll fit in Collab, by the way, on the smaller 15 or 16 gigabyte T4s. This is the type of attention. It's using XFormers. The model paths, so it's going to download, I think from Hugging Face, the MEMO model. Later we'll inference on a fine-tuned model. These are the variational autoencoder. That's for going from the image into vectors. Wave to vec is for the sound, is for converting a wave into a vector representation, so converting your audio into vector. There's also the same for converting emotion. So there's an emotion representation extracted from the image, and that's also converted into vector. So we've got the inference file here specified, and with that we can run inference. And I should have run it first actually, because it would have been going while I was explaining. Now, if you want to try and run in higher quality, then you can use instead the inference high res here. What's the difference? Well, you could potentially increase the number of inference steps. So instead of diffusing out in 20 steps, you diffuse out in just, you diffuse out in 50 steps instead. You can consider adding, accentuating or de-emphasizing the role of the image that you're providing. You could also potentially increase frames per second. I'm not sure that helps too much because the model is trained in 30 frames per second, and we also view images. It's hard to perceive anything faster than 30 frames per second. So yeah, the main thing I'd recommend playing around with is the number of inference steps to see if you get a smoother generation. Now we're running the basic inference here using the basic inference YAML file. You can see we're downloading models, and I will just briefly describe the architecture while we're waiting on that download. So when I run the inference, I added to the script the ability to print out the model architectures. And let's first look at the whole pipeline. So the pipeline describes all of the individual models within. This is the video pipeline, and it includes a few things. So it has the image projection. So this takes the image, converts it into a vector representation. There's also the reference net. This is taking then the representations of the images and the pass frames. It's that UNet that is allowing information to be fed down into the larger diffusion net, which is this one here. So we have those two diffusion nets. Let me just show you those in the paper here. So if I go across to the paper, here is the reference net, and it's feeding information from the images down into the diffusion net, which is this diffusion net here. There's then the scheduler. So this is specific for inference. This is defining the parameters of the steps that are used in diffusing out the image. We've got 20 steps as we're currently running, and this is the variational autoencoder. And if you check in more detail, you can see the architectures. So the audio projection, for example, is very simple. There's a projection that goes from the audio and converts, basically transforms the vectors into a form that can be accepted by the diffusion net. And you can see here it's got 3 linear layers in it, so it's quite simple. There's an image projection model as well. This is even simpler. It's just got 1 linear layer. And then you've got the very many multi-layered diffusion net and reference net. So the diffusion net, for example, it's got many layers here. This is the cross attention down block. You can see it's a transformer architecture because we've got the Q, K, and V, and there are many of these blocks. You can go 0, 1, 2, 3. Then the up blocks 1, 2, 3, and then the mid blocks. There actually seems only to be fewer of the mid blocks here. And this architecture is very similar to the diffusion net. So we've got down blocks, up blocks. These are transformer type architectures that are being used for diffusion. Okay, so in the meantime, let's see how inference is doing. We're currently doing inference, so the models have been loaded. You can see it's going through 20 diffusion steps here, and it's got to go through 20 diffusion steps for every set of 16 frames. So for every second of video generated, we need to have roughly 2 full diffusion processes. So that means if we've 24 seconds of video to make, because that's the length of my audio, it's going to take us 24 times 2, 48 times we'll have to go through 20 steps. And you can see each of the 20 steps is taking about 2.5 seconds. So that means 2.5 times 48. So very roughly, it's going to take 2 minutes, 3 minutes to diffuse out one full video here. Now, as we wait for that to finish, just to note that you can download a pre-trained model. I've included scripts here both for downloading models and for uploading models with push to hub. And these are also copied within the MEMO folder, so they can be run from within the MEMO folder. And I'll just show you for a quick example, a model that Rohan and I fine-tuned. This is a video done in collaboration with Rohan Sharma under the Trellis Developer Collab program. You can check that out, by the way, on trellis.com if you're a talented developer and you want to collaborate on a Trellis product and video. So here's a model that was fine-tuned fully by Rohan, and it's available on Hugging Face, although I think it is gated. But I'll just show you here the model. There's no model card, but it's been pushed up with a checkpoint, and it does contain each of the key models. So the audio projection, the diffusion net, the image projection, and the reference net here. And then because this is a checkpoint, it has the optimizer states as well. So if you have pushed a model up to hub, you can then download it using this download model script, and it will download it into the output folder and then allow you to run inference on it like this here. And actually, I am going to download one of the models because I want to do some inference to create a video for today. And I'm going to do that by just going to the Trellis org and finding the model that I want, which is the Avatar LoRa model. This is a model I've fine-tuned using LoRa. I did it yesterday. I'll explain the fine-tuning process in a bit. But for now, let me just set this up here. I will need a Hugging Face hub token. So I'm going to open up a new terminal here, CD into AI Avatar, and actually CD even into the MEMO folder. And I'm going to briefly add in my Hugging Face token here. And with my Hugging Face token in there, I think I can just download this in parallel to the inference that's happening. So I want to download this and I want to put it into the fine-tune folder. So the checkpoint folder is not found. So with the key exported, I need to make sure I'm still in the MEMO folder and I can run the download. So you can see that the files are being downloaded now, and they should be downloaded into the MEMO folder here underneath outputs and then fine-tune. And you can see here where the model is being downloaded. And given that model is being downloaded, it's going to allow me to now run an inference using this fine-tuned model rather than using the unfine-tuned model. And actually, I'm going to just get that started by running an inference script here. So we'll run inference, and the image path we want to run on is the same as what we ran with earlier up here. So we want to run with this, but this time we're going to put it to an output of LoRa because that's what we're looking for. And note that when we rerun this inference, we need to update our inference YAML file. So I'll go to MEMO configs, then I'll go to the inference, and I'm going to update this so that instead of running the default model, we're going to run the LoRa model here in outputs. So you can see it should be, model name should be outputs. Sorry, I got that wrong. It'll be fine-tune, and the model should directly be there, I think. So this all looks in good shape, and I think we're ready to run inference on this. So basically what I'm doing now is using my LoRa fine-tuned model, and we'll see if the LoRa model performs any better than the original model. Meanwhile, the original model should be finished at this point, and it is finished, and it should be saved. So it's saved in the 0-shot folder. So if I go up to the outputs here, I've got my original model, I've got 0-shot, and here I've got the video. So let's take a quick look at this. In this video, I'll explain how to create and fine-tune an AI avatar. Yes, I am an avatar of Ronan, created using only a starting image and a voice recording. You'll be able to do the same, whether it's for... Now, it's not bad. Image and a voice recording. Maybe there's a little lack of smoothness there, which could be helped by doing higher frames per second. You'll be able to do the same, whether it's for a conversational assistant or for entertainment purposes. And it is maybe a bit jumpy. So that maybe is, sorry, I said frames per second, but I meant diffusion steps. That might be possible to improve. But you can see, I'll then show you how to further improve. Already without any kind of fine tuning, this model is pretty good. Now I can see, for example, yes, if I look at certain parts, like here with my teeth do not look like this. They look kind of like kids' teeth here, and my teeth are just not as good as the top row here. So I can see there are differences, and that's where the fine tuning is going to come into play. And already, when we run this model, you can see it's currently inferencing. It's at generating step 6 out of 45. It's a 24-second video. That's why there's roughly double, because it's 16 frames generated per iteration. So roughly 48-ish frames that need to be made, a bit less than that. That's why it's 45. So we'll see the results of this in a moment. But in the meantime, let me talk a bit about fine-tuning and how you can do this. And broadly speaking, with fine-tuning, what you're doing is you're going to improve the weights of the model using video samples that you have. And there are two ways to do this. There's full fine-tuning, where you update all of the weights described in the architecture here, or certain modules within. And then there's LoRa fine-tuning, where you're going to update adapters that are they're smaller representations of those larger matrices that will essentially be plugged on. And the benefit of doing LoRa is that, well, it takes less memory, less computation on the back pass, but also it can avoid overfitting, because you're just training a lower rank representation. So that stops it from trying to granularly change the matrices just to fit your training examples in a way that won't generalize to inference. So to run the fine-tuning, you're going to run finetune.py, which is here in the MEMO folder, finetune.py right here. And that finetune.py is going to take in a YAML file that will define the configuration. So let me describe the key settings for setting up fine-tuning, and then I'll describe the key settings if you want to do LoRa fine-tuning. And LoRa fine-tuning will be done using finetune-LoRa. This is a Trellis developed script that allows you to do LoRa fine-tuning. And I did both, so I'll show you the results from both of them. So first, let's look through the YAML file for fine-tuning, and then we'll look through the fine-tuning, the YAML file for the LoRa. So when fine-tuning, you can set up a project name, an output directory. Whether you're resuming from a checkpoint, by default, we'll just train the base model. You need to define the base model you're training. This is the model on Hugging Face, the one we've inferenced for zero shot. You need to define the variational autoencoder, which, by the way, is initialized from a stable diffusion model. Now, we're going to use gradient checkpointing. This is going to save memory. It means that we won't store all the activations when we do a forward pass. Every forward pass, we won't store all the activations for the backward pass. We'll recompute them, which saves on memory. We're going to set gradient accumulation to 1. So basically, with batch size 1 and gradient accumulation 1, this will keep our memory requirements low. And the fact that this is 1 means we're granularly updating the model on every single forward pass. So every video is going to result in a model update. This means it might be more noisy because we're updating for every video. We're not averaging across videos, but it also means we're going to ingrain more of the detail of each individual video. Typically, if you have a small data set, you're going to want to set this to a low value. If you had a very large data set, like say 10,000 or even 1,000, then you would want a virtual batch size, which is the product of these two, to be probably at least maybe 32. We're going to train for 500 steps. Now, 500 steps on a data set, and our data set is only going to be about, say, 16 images. 500 steps means we're training for a lot of epochs. In fact, epochs here is not set because it's -1. And the reason you train for so many epochs in diffusion is because on every forward pass, you are actually only training part of the diffusion. Let me show you what I mean. So in this, let me find the presentation here. Every time you do a forward pass on a diffusion model, you don't simulate every single diffusion step. So if you're doing 20 steps to diffuse out a real image, you're not doing all of those steps on a forward pass for training. You're actually only doing one random step. So if you had normally 20 steps, you're actually just diffusing one of those random 20 steps. And so if you do one epoch, as you think of it like training an LLM, it's not really one epoch because you're only sampling a very specific part of those steps, only one of those steps. So actually, if you're doing 20 diffusion steps, this is a very rough way of thinking about it. When you were training for multiple epochs, you probably need to train for like 20 epochs instead if you're of normally doing for one epoch. So here, my effective epochs, this is very loose, but you could think of it as dividing by 20 or say 25 for the maths. And that would mean we're actually not training for 500. We're really training for 500 steps. We're not training for 500 over 16 epochs. We're actually training for 500 over 16 over 20, which is not 1000 according to autocomplete. It would be 500 divided by 320, which is roughly like 1.6. So we're actually training for more like 1.6 effective epochs. That's very approximate, but intuitively, it's the right direction to think about it. So here, we're going to use XFormers for attention. We're going to save the last two checkpoints. We're going to checkpoint, which just means we're going to save every 250 steps, which is here. Probably should just be moved up to here, so it's about it. So we're going to save a checkpoint on 250 mark. We'll save it, and then we'll also save on 500. The learning rate, we'll use 1e minus 5, which is what was used for training the MEMO model, so we're not going to change that. We're going to cap the gradient norm. So if it goes above 1, we're just going to clip it. We're not going to use any learning rate scaling. We'll use a constant learning rate. I've adjusted this from the default to cosine in the repo because I think I find constant gives better performance and easier to restart training. We'll use 25 warm-up steps, although that's not really that critical. It just means your learning rate goes up before it hits the peak target value. What else to highlight here? You can save memory on the optimizer by using 8-bit Atom. Note that most of the memory here, though, I think is for the forward pass. It's not for the backward. Well, let me say that again. No, that's not true. There is going to be memory that's for the base model being loaded into memory, and then there's memory for the optimizer states. And what using 8-bit Atom does is it compresses by about a factor of 4 the size of your optimizer states because it uses 8-bit instead of 32. So you can use that to save further memory, although it looks like I'm not using that here. These are all optimizer parameters here. These are the workers for loading the data. I mentioned the checkpointing steps. This is the data spec. So you've got the height and width in pixels, number of pass frames, sample frames. Probably want to match this to your inference choice. And we also will look at the training. So this is critical here. This is setting up which modules we want to train. You can decide to train the reference net, the diffusion net. We're doing all of them, the image projector and the audio projection. And within those, you actually have to specify the modules within the reference and diffusion net that are going to be trained. You don't actually have to do that for the image and audio net if you read the code, but you do have to do it for the diffusion and reference net. If you try to train the reference net and you don't include these, well, that's not going to do anything because there are no motion modules or audio modules in the diffusion net, or rather in the reference net. You can check that here. If you look at the reference net, it does have these to Q, to K, to V, but there's no audio or motion modules. Whereas here you can check for the motion modules, and that is a named module. So that will train this module if you specify it in the fine-tune YAML. So this is training fairly broadly across all of the aspects. Here we have a LoRa alpha, but this is not relevant actually. If you were doing standard training, it's only relevant if you're going to do LoRa training, which I'll talk about in a moment. And these are some further ratios. I actually haven't dug in exactly to the meaning of these, but I've left them to their default values. So with this all set, we should be in a position to start the fine tuning. But first we need to process all of our videos. So for that, I have grabbed a set of videos from my own YouTube videos, and I'm going to place them within the raw video folder. Now you can directly place them in the video folder, but my videos are landscape, so they need to be pre-processed to be square. And so I've provided a script that will move them from landscape to square. And so if I go to MEMO and I go to assets, you can see there's already some content here, but I'm going to want to add in a new folder that's called raw video. And then I'm going to put my videos here. Now, I did do this on 16 videos. I'm not going to put all the videos in now, but I'm going to put in a few sample videos just so you can see what happens. So I'll copy in 3 sample videos to raw video here. And then I'm going to convert them to square videos. So I need to wait until they're uploaded before I can run this script. And this script will find all the video files in the raw video folder, crop them to a square, resize them, ensure the audio is included, and save them to MEMO assets video folder, which is the folder we would put the raw videos in if they had already been formatted. Then we'll calculate the duration of the videos. I actually trained on about 4 minutes. I think for the full fine-tuning, Rohan trained on 3 minutes. So when I show you the full fine-tuning videos, that's trained on 3 minutes. The LoRa is trained on 4 minutes. I just added in a few other videos. And when you do the training, whether it's LoRa or standard, you're first going to pre-process the videos. This means converting them, I think even into embedding form, which will save you time when you're then going to run the training scripts, because you're not going to have to do the data processing. So it looks like these 3 videos are almost uploaded, and I can convert them into square videos if that's true. Here we've got, so you can see a landscape 9-second video, a landscape 19-second video. And yeah, these are just from my past Trellis channel videos. And we have a 3rd video here, which is, oh, that's a really long video actually. So I don't want to process that one. And the reason is every clip needs to be shorter than 30 seconds. I should have said that. And it ideally is a clean video that starts off with some speech pretty soon. And then when it finishes, it shouldn't have too much blank space. So I'm going to delete that really long video because it's too long. And I'll just show you quickly a video here that is a sample. So this is a video on how you can add read-only memory, which allows you to improve reasoning performance and also achieve effectively longer context lengths. Okay, now there are 2 things I'll critique on this sample that I've provided, which is first, you can see it's pulling in this transition. And yeah, that's a bad sample to use because this is going to add noise to the data. So that's actually not good to add in. And there's one other thing I didn't like about this video too, which is if you look at the start video and how you can add read-only memory, which allows you, yeah, so right there's a little cut in the clip, and that's because I cut out some blank space in my video originally when I made it, but you don't want that cut because that cut is going to be not realistic in terms of the type of generation you want to mimic. So ideally you want to have much cleaner videos. Let's see if this one here is any better. But you should know that the highest quality implementations of search with LLMs will also use traditional techniques that are based on keyword search. So this video looks pretty good. Let's just check the end. Yeah, again, this is not good. So the fact that this is coming in is probably going to cause maybe color issues. So yeah, keep that in mind when you're doing training. I did actually record some cleanish videos that don't have these issues. And I mostly use those clean videos. I mixed in a few slightly non-clean videos into the LoRa fine-tuning set. Either way, I have 2 videos here. I did use 16, but let's just work with these 2 for the purpose of showing you how to convert the videos into the right size dimension. So here, it looks like I've converted 2 videos. And with the videos converted into the square format, I can then calculate the duration of the videos. And the total duration of these is 28 seconds. And then I can pre-process the videos so that the embeddings are ready to go. And when they're ready to go, they'll be placed, I think, in the output folder. And they should be placed in the output folder under embeddings. So let's see if that happens. Sorry, not the output folder, the assets folder under embeddings. Yeah, so there we have them. And you can see we have a file. Yeah, these are PT files, and they contain the embeddings that we need for audio, for emotion, and for the face. And you've also got the raw WAV files here. So with everything pre-processed, you can then start the fine-tuning, and you can run the fine-tuning either using the full fine-tuning I described or the LoRa fine-tuning, which I'll describe in a moment. And once you have run the fine-tuning script, it's going to save the logs and you can view them using TensorBoard. In fact, why don't we just run a very quick fine-tuning here? We can do it. Let's do a LoRa fine-tune, which gives me the opportunity to describe the LoRa fine-tune script here. So the only difference with the YAML file is actually that we define the LoRa alpha, which is the acceleration of the learning rate. Basically, if you use these smaller adapters, you can train them much faster. And this you can think of as a scaling factor for the learning rate of 1e minus 5. Now, actually, this ends up being multiplied by 1 over the rank. So it's really 256 divided by the rank of the smaller matrices, which we choose as 16 hard-coded in the script. So really, the acceleration of the learning rate is a factor of 16. It's not a factor of 256 here. Now, this LoRa alpha is important when you go to the fine-tuning script. If we just search for it here, let's just search for LoRa alpha. And you can see that it's setting the LoRa alpha within the LoRa configuration, which defines how those adapter matrices are set up to be plugged on to the base matrices. Also in the LoRa config, we define the rank, that's the size of these adapter matrices, the modules to target, and then, we set some defaults of having no dropout or bias. So this LoRa config is used to create the adapters, not just for the diffusion net. We can also search and find the LoRa config for the reference net. So here, diffusion net, reference net. This is the audio projection, and then for the image projection. So we're applying LoRa adapters in each case. Now, I won't go through the full fine-tuning scripts. They're quite similar for fine-tuning and for LoRa, but for LoRa, there are two differences. One is when we load the models, we then freeze everything except for the LoRa adapters that we create for each of the parts of the model. And furthermore, at the end of training, we're going to merge the LoRa adapters back onto the main model. So if we search from the end, you can see here that if there are adapters, they're going to be merged and then the model will be saved. The checkpoints will be saved as adapters, but the model will be saved in its entirety as a merged model. So with those two scripts done, I'm just going to show you how to run fine-tuning. So we'll run both of these scripts, the fine-tune one, which will use fine-tune.yaml, and then the one that uses fine-tune-LoRa. And note that when I define my YAML files here for doing the fine-tuning, I have reduced the number of steps, just so I can run it quickly for you here now. We've got max steps of 10. We've got one warm-up and then checkpointing of, I think, 5 steps. Let's see where that's set. Let's search for number 5. And actually, for checkpointing, I'm saving every 10 steps, so I'm just going to save right at the end. And I'm going to run that script. And by the way, I'll do the same for LoRa fine-tuning. I'll just train for 10 steps. Now, since there are only 2 videos, that means that is effectively 5 epochs. So when you look here at the training, let's take a quick look here. I need to expand. You can see we've 5 epochs, 2 examples. Train batch size is 1 gradient accumulation. And we're going to run for 10 steps. So this training is running. We can inspect the logs here just by running TensorBoard and pointing it to the right directory, which will be fine-tune short, or in the case of LoRa, it would be fine-tune LoRa-short. Now, I could show you the logs. They won't be that interesting because I'm doing just a few steps, but we will check them just for educational purposes when we run the LoRa fine-tuning. Here you can see the fine-tuning's over, and it's saving the final model within the outputs folder. It's saving it to fine-tune short, and it's saving it to the final model here. And you can see the checkpoint is saved right here. So this is the full model because we're not using LoRa. Now, if I run with LoRa, which is this script here, and you need to install PEFT, which is parameter efficient fine-tuning, it's going to start off by applying the LoRa adapters, and it should even tell us how many trainable modules there are. So it's going to apply the adapters to these modules here, motion, audio, 2Q, 2K, 2V, and it's going to apply it in the audio projection to proj 1, proj 2, proj 3, and in the image projection to proj. And this makes sense because when we look at the audio projection, you can see there are 3 linear layers to apply it to, and in the image, there's just 1, which is proj. So this all makes sense. And the total trainable parameters are 29 million. we can see a breakdown, I think, according to the models. So here's the diffusion net. It's 1.7 billion, 1.3% trainable. The reference net is 862 million, 0.6 trainable, and about 3% of the projection modules are trainable. Notice this is really quite small. The image projection is just 57,000 parameters. So we're training through all these steps, and I said I would show you how to run TensorBoard. So let's do that now. We'll run TensorBoard for fine-tune LoRa short. It's over, so I can just run it in the same terminal. We're going to point at the outputs folder, LoRa fine-tune short. And I'm going to click now. Hopefully it should let me click. Localhost. Won't let me click, but I can copy paste here. And you can see I loaded it earlier. And yeah, here we're moving through the epochs. Here we've got the grad norm for 10 steps. It's less than 1, so it looks fairly stable. And here we have the training loss, which goes up initially and goes down. Now, I did train this for 100 steps using LoRa, and I did it on 16 different videos. And what I can tell you is you actually see a similar pattern here at the start, but you see that this will fall, and it actually tends to stabilize. As you go from 100 to 500, it stays relatively flat. That doesn't mean you're not encoding information though, because I did find the resemblance was better at 500 than 100. But at 100 steps, you'll start to see some influence on the results. Now, to see the quality of your fine-tune model, you need to run inference on it. And the way the models are stored is within the output folders. We have one in fine-tune short. It's stored in final model. That's the final model here. Whereas in LoRa short, it's stored, let's just see here. It's storing the checkpoint, and it should also store the final merged model. Yeah, the final merged model here is within final model. And if we just check the checkpoints in the audio projection, you can see in the checkpoint, it's an adapter. It's not a full model, but in the final model, it is a full model. It's not an adapter. So this all makes sense. Now, I want to inference the model that I trained for more steps, for 500 steps. I've actually downloaded that model to the fine-tune model earlier in this video, and you can see it's fully downloaded here. So I want to run inference on that model, that one I downloaded. So in inference highres.yaml, I need to specify my model as being in the correct path. And the correct path it should be is outputs fine-tune. That's where my model weights are located. And I'm going to inference in high res, which means I'm going to use 50 inference steps. I'll use a classifier free guidance scale of 5, which is a bit higher than my default of 3.5. I want to make it look a bit more like my original image. And then I'll run that script. And I ran it earlier. It takes about 20 minutes to do the high res because you're inferencing 20 steps for every iteration. Sorry, 50 instead of 20. I also ran it with just standard res, so 20 inference steps. And I got those results, which are currently in the outputs folder. If I go to outputs and I look at LoRa, you can see there's a video here. And if I look at high res, there's a video here. I can show you a quick example. This is the video you saw right at the start of this video. In this video, I'll explain how to create and fine-tune an AI avatar. Yes, I am an avatar. Once you're done with that, you can push your model up to Hugging Face Hub by specifying a repo name, the checkpoint directory to pull from, or if you're just pulling the final model, it would be like this. And you can specify whether you want that to be public or private. Now, I want to analyze a bit the performance of these videos. And to do that, I'm going to set them up in a grid, a 4x4 grid. And I want to have the original. I want to have the zero shot, which is without fine-tuning. Then a high-res version, which is both fine-tuned and high-res. And then lastly, just, sorry, I deleted that. Just the fine-tuned version that's going to use the LoRa model. And here are the labels I'm going to set up. You'll see these appear on the video. So when I run this create comparison, we can close down these terminals now. Running video comparison is going to just take all of those videos and bump them into one final video. That's called comparison.mp4. And here we are after 16 seconds. It's created our video. So original, zero shot. And let me turn off sound for a second. And then we have LoRa high res and LoRa. And you can just see here, without the sound, the comparison. The big difference with the original is that the head movement is a lot more in the original. That's because if you look at any output from MEMO, it just doesn't have much head movement in its data set, I think. There are 600 hours that MEMO was trained on. If you wanted to get better head movement, you need to use at least 100 hours is my guess, maybe even more, to get good head movements. Another thing you can see is the difference between the high res and the LoRa. There's a little bit more flicker in the standard LoRa compared to the high res. So probably this is a bit better quality, the LoRa high res. Now, the difference between zero shot and the fine tunes can be a little subtle until you pause the video. And if you pause it at certain moments, what you'll find is that there's a bit more of a similarity between the original and between the zero shot. Now, here in all of these cases, I think there's not a huge amount of difference. Possibly you could say the zero shot, the mouth is a bit too pursed here. Let's go back to an earlier point. Now, here you can see the mouth is a bit more separated, maybe too separated in the fine tune, whereas in zero shot, it's maybe too closed. In this case here, fairly similar. This case here, fairly similar. If anything, the mouth is more open in the zero shot. In this case here, potentially these are a little bit more similar than the zero shot. So you can look through and see which attributes are being passed on. But yeah, I will say it can be difficult to see very large differences between zero shot and the fine tune, which is kind of testament to the quality that's achievable using the zero shot. And only if you really care about very small specific differences like mouth shape, I think you'll find a little bit better performance in these fine tunes than using that zero shot there. And that pretty much covers this video for fine tuning and inferencing avatar models. If you do want to fine tune with better quality, I'd suggest trying more vid data than just 4 minutes. I used 4 minutes for LoRa. Rohan had used 3 minutes on the full fine tune that we did. And I recommend as well having very clean videos. I showed you a few of my videos that were not clean, although the majority of them were clean because I made them specifically for this purpose and carefully manually reviewed them. So that's probably going to give you the best results. You could also play around with the learning rate. I didn't see the gradient norm go above 1, so potentially there's room to increase the LoRa alpha, which is equivalent effectively to raising the learning rate in order to get faster convergence of your model during fine-tuning. All right, folks, that is the overview of how to create and fine-tune your own video avatars. Many thanks to Rohan Sharma, who was key in this collaboration, helped out a lot with the fine-tuning and inference and comparing the quality of different approaches. This was done under the Trellis Developer Collaboration Program. You can find out more about that over on trellis.com if you're a talented developer and are interested in doing a collab on a product and video like this. In the meantime, folks, you can find materials on trellis.com/advanced-vision and let me know any questions below in the comments. Cheers.